Okay, so let's now see this next one. Here we are given a commutative ring which is finite and it has no zero divisors. Also, it's given that the ring has at least two elements. That means it's not the zero ring which has only the zero element in it. It's not that. Then we have to prove that it has a unity, an identity with respect to multiplication. Okay, so here the solution goes like this. So first of all, what we do in the solution, we consider the set of all non-zero elements in the ring, which is a finite non-empty set. It is finite because the ring is finite, and it is non-empty because the ring has at least two elements. So let AN be the set of all non-zero elements in the ring. And we also mention that fact that S is non-empty. Note that S is not equal to the empty set since there are at least two elements in the ring. Okay, so we know that there is something, at least something in S, and all of these elements are non-zero. Now what we do, now consider the elements A1, 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 A2, A1, A3, like that. So what we are doing is that we are multiplying all the elements of S by this one element A1, which we have just simply chosen to be any random element of S. So we have decided why not A1. If you want, you can choose A2 also. Nothing will essentially change. So we are considering these products of all the elements of S with A1, including A1 also itself, A1n. Now because the ring after all is closed under multiplication, so these are all going to be elements in the ring. These are all elements in the ring. That of course is something trivial, but what is a little more non-trivial is that none of them is zero. But why? None of them is zero. The reason is that since the ring has no zero divisor. That is the reason, because say you take any, say a1 a2 is 0, contrary to what we are writing here. Suppose a1 a2 is 0, then what goes wrong? See, a1 and a2 individually being elements of S are non-zero, because S is the set of all non-zero elements in the ring. But now if their product becomes 0, then by definition both of them will be 0 divisors, which is what the ring does not have. That is the hypothesis. So none of these products can be equal to 0. So that means what? That all of these things are in the ring and all of them are non-zero. That means all of these must belong to S, because this is the set of all non-zero elements in the ring. Hence, these all belong to S. Okay. Now next what we want to ascertain is that actually they are all distinct. Okay. There is no two such different elements in the list which actually are the same thing. That is not happening here. In this list, actually we are looking at n different or n distinct elements in the ring. But suppose that is not the case. Now suppose A1 AI is equal to A1 AJ for some integers I and j, satisfying these inequalities, that is we are writing at once. That means I and j both lie in this range and they are not equal, that is they are different. So one of them will of course be less than the other. Without losing generality, we have assumed that I is less than j. Then using the distributive law and all the other elementary properties that are there in a ring, you can write from this equation this. Now since the ring has no zero divisor and A1 is non-zero, being an element in S, so the other factor has to be equal to 0. Has no zero divisor and A1 is not equal to 0, we must have AI minus AJ equal to 0 or AI equal to AJ. But this is a contradiction, because you see, when we wrote down the elements of the set S, then all these A1, A2, these were considered to be distinct elements. So since I and J are distinct, AI and AJ should also be distinct elements in S, which is not what we are getting here. So that means this is something wrong. But this is a contradiction. A contradiction to how the elements of S have been written. So, our last supposition is wrong. That means i.e. such a thing cannot happen, which means what? That these are all n distinct elements. A1, A2, A1, AN are all distinct. Okay. So how many elements do you see in this list? N. And how many elements are there in S? N. And all of these elements are also in S. So that just simply means that S consists of these elements. So these elements in fact are nothing but the original AIs in some order. So we write and by writing this, we do not mean that A1 is equal to A1, A1 A2 is equal to A2. No, maybe in some order that may also be true, who knows, but S will consist of these elements and these are the original AIs in some order. Okay, now since A1 originally itself is coming from S, so in this list A1 itself will appear somewhere. So A1 will be equal to A1 AI for some I in the from among the available indices, that is from 1 through n. Now for any non-zero element x in our ring, any non-zero element x, so that means what we are doing is that we are actually considering an element from capital S, because capital S is the set of all non-zero elements in the ring. So let x be any non-zero element in the ring. So x will look like this. Because that's how the elements of S look like. We have found that. Okay. Then XAI. XAI is then equal to A1 AK AI, but because your ring multiplication is associative, so this is A1 AK AI, but it's given that the ring is commutative as well, so you can change the order. A1 AI AK. Then you apply associativity once more, you get A1 AI AK. But A1 AI is just A1, So you are getting A1 AK back, which just simply means that you are getting X back. So you have shown that XAI is equal to X. And because of the fact that the ring is commutative, AIX is also equal to X. Hence, just to be absolutely sure about what we are writing, let us write that also. No matter how trivial it may look, that AIX is also equal to X. So we have shown that AI acts as a unity in the ring. That is, if we multiply it with any non-zero element, then we get the non-zero element back in any order. But what about the zero element? What about 0? For that, actually nothing has to be done, but still, let's just simply show that also. 0 AI is of course equal to 0, and that is equal to AI 0. So that just simply tells us that AI is a unity in our ring, and that's what we were trying to find. Thus, AI is a unity in the ring. Okay, so that means we have found a unity. Next, suppose that A and B belong to a commutative ring and AB, the product of A and B, is a zero divisor. That is given. Show that either A or B is a zero divisor. And this one is not very difficult, and it's not very long also. Let's see how we can solve this. So this time our ring is again commutative, but unlike the previous one, now it's given that AB is a zero divisor. So we have to prove that either A is a zero divisor or B is a zero divisor. So in the beginning we just notice something. Note that it is given that AP is a zero divisor. So by definition of zero divisors, AB is a non-zero element in the ring. That should be there first of all. And because of that, a consequence that AB is non-zero is that both A and B are non-zero. So we first write that since AB is a zero divisor AB is non-zero and hence A is non-zero and B is non-zero. But then of course we write the main condition for AB being a zero divisor. Also, there exists an element C also not equal to 0 in the ring such that AB times C is equal to 0. Because we call a non-zero element a zero divisor if there exists another non-zero element which may or may not be equal to the original element such that their product is 0, right? Then using the associativity of multiplication in the ring, you have this A times BC is equal to 0. Now we know that AB is non-zero, but we do not know, and we also know that C is non-zero, but we do not know whether BC is non-zero or not. It may be non-zero, it may be 0, and accordingly we will have two cases. Now, if BC is not equal to 0, then looking at this equation, what do we see? BC, if it is non-zero, then it's a non-zero element in the ring, and A originally is already non-zero, but their product is 0. But then that means what? That just simply means that A is a zero divisor. So we write, now if BC is not equal to 0, then A is a zero divisor. Okay, that is when BC is non-zero. But what happens if BC is 0? If BC is 0, then you look at this equation itself. B is non-zero, C is non-zero, but their product is 0. That means what? B is a zero divisor. And that just completes the solution, because we were supposed to show that either A or B is a zero divisor, which is what we have managed to show. So that is the solution. Let's see another one. Suppose that R is a commutative ring without, okay, so we have again come back to without zero divisors. Show that all the non-zero elements all the non-zero elements of R have the same additive order. Have the same additive order. Now, what is it that we should do here? I mean, what is being asked? So what we have is this. You know that a ring has two operations, addition and multiplication. Now this part of the ring is an abelian group that you already know. So what we are seeing here is that, say we take two elements in this ring, then you can of course consider them as elements in this abelian group and say both of them are non-zero. A is non-zero, B is also non-zero. Then they will have the same order as elements in this group, because being an element in a group, every element has some order. Either that order is infinite or that order is finite. Whatever the case is, you have to prove that both the elements have the same order. Okay, so let's see. To say that the group we are considering here is of course the ring, that is the underlying set under addition. So the author is saying additive order. Okay, so let A and B be two elements in the ring from which we have, say, removed 0. So this just tells us that A and B are both non-zero elements in the ring. Okay. And also one more thing is given, is that the ring is commutative without, of course, the ring is not just simply any ring, it's a commutative ring without zero divisors. So what we first do, suppose A has infinite additive order and B has finite additive order N. Okay, so that means we are supposing something that the exercise is claiming is not true. So let us first of all suppose that A and B have, one of them has infinite order and the other one has finite order N. So that means this N is a positive integer. Okay, now consider this following calculation. because B has order n. So then n yx, oh, why am I taking y? It's A and B, no? NBA. We know that in a commutative ring we can have this. This is something that we already saw in a previous exercise. And then that is equal to 0, A, which is equal to 0. Okay, by the way, why do we have NB equal to 0? Because you see that this NB is in fact b to the power n, the integral power, where the element of which you are taking the integral power is b and the exponent is n in the additive group R plus. But I think the author has, now I remember something. There, because of a possible confusion between the ring multiplication and this type of multiplication, I think it was we are supposed to write a dot here. So let me write it like this. So this is n dot BA means we are considering the nth power of the group element BA in this additive group. But we already know that in a ring this is equal to this. Now this is equal to the identity in this group, which is what? Which is the 0 element. So we do not write a dot here because this is the 0 ring element and this is the ring element A, and their product of course is 0. Okay. So what does this tell us? This implies but instead of writing n dot BA, we could have written n dot AB also, because we are dealing with a commutative ring. Or I could have started the calculation like this. NA times B is equal to, or rather n dot A times B is equal to n dot AB. That is equal to n dot BA, but we have already found that that is equal to the 0 element in the ring. Right. So now looking at the first term and this last term in this series of equalities, what do we see? We see that a product of two ring elements is 0. One of them is n dot A and the other one is B. But B, according to our choice, is a non-zero element and the ring has no 0 divisor. So that means n dot A must be equal to 0. Since R has no 0 divisor, we must have n dot A equal to 0. But that means what? That just simply means that A cannot be of infinite additive order, because we have already found a positive integer n for which n dot A is equal to 0. And this means that the order of A is less than or equal to n in the additive group of the ring. But this is a contradiction to the fact that A has infinite additive order. And this contradiction has stemmed from our supposition that we have two such elements, one having finite order and the other one having infinite order, which we cannot have. Hence, our last supposition is wrong. And as a consequence, either both of them will have infinite order or both of them will have finite order. i.e., either both A and B have infinite order means additive. Okay, let me just write additive. Or both of them have finite additive order. Now, if both of them have infinite additive order, then there is nothing else to do because both have infinite order. But if both of them have finite order, then we are not done yet. We have to then still show that their orders are the same positive integer. And now that we try to show. Now, let A and B both have finite, it will be orders, finite orders. Let originally we took the order of B as, okay, so let me just do it like that. So let M be the order of A and N be the order of B, just like before. But now our supposition is that they are not the same, say. Then we will try to arrive at another contradiction. Okay. Now suppose, without losing generality, that M is less than N. Okay, if M is less than N, then which one should I take? I mean, if I take M is less than N, so with M I should take B. Okay. With M, if I take B, that means I have to take B as well as A. So the larger one is this one. Okay, let me try like this. Then 0 is equal to 0B simple ring calculation, but because the order of A is m, this is m dot A times B, because m dot A will be 0. But again, just like before, this is nothing but m dot AB. But using the fact that the ring is a commutative ring, we can, or instead of using commutativity or anything like that, you can just write A times m dot B, because this is also true in a ring. M dot AB is A times m dot B. M is after all a positive integer. In fact, it does not matter that m is a positive integer. For any integer, this is true in a ring, and this is something we proved in a previous exercise. Okay, now again we look at this equation. This product in the ring is equal to 0. Now note that A itself has been chosen to be non-zero, B also is non-zero, and the ring has no zero divisor. So we write again, since A is non-zero and R has, okay, let me just check if R, yes, R is without zero divisors. R has no zero. I want to make sure that this hypothesis is there, because similar exercises are there, no, 3 or 4 of them, so I may get confused. So there is no zero divisor and A is non-zero, so this equation implies we must have m dot B equal to 0. But is that possible? Note that the order of B, the additive order of B is n. So that means n is the smallest positive integer for which n dot B is equal to 0. Here, however, m is a positive integer which is smaller than n, and still m dot B is equal to 0. But that cannot be, because this is violating the minimality of n as the order of B. But this contradicts, this just simply contradicts this fact that n is the order of B. So our last supposition is wrong again. I.e., this cannot be true. That is, m cannot be less than n. Similarly, n cannot be less than m. Just switch the roles of A and B, you get this. So that means they must be equal, and that's what we wanted to show. That is, whenever you have two non-zero elements and their additive orders are both finite, then they have to be the same order. And this completes the solution. And let's just end things here itself for tonight. We will continue with more solutions in the next Gallian ring update. And tomorrow, of course, we are going to continue our study of analysis, where we have just completed the proof of Fubini's theorem for infinite sums, for infinite series. And tomorrow we are going to see that thing that I was talking about back then, a characterization of absolute convergence of such infinite, that is sums over infinite sets. And then we will see where we can go from there. So that's just it. I wrap things up with this for tonight, and tomorrow let's see analysis. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.